Hi there, in today's video we're going to be going over progress check for and look at solutions for them. So the first question, we had an integration by substitution question, okay, where we're told to integrate the integral of x cubed over 1 plus x to the power 8 with respect to x, but use the substitution t equals x to the power 4. Okay, so what we actually do with this question, we start off with the substitution itself. So if we're told t equals x to the power 4, then if I differentiate that, so it'll be dt with respect to dx, then I get 4x cubed. Okay, now we've got a dx involved in our question, so if I rearrange that for dx, I would end up with dt over 4x cubed there. Okay, and that's what I'm going to be using to help me with my substitution. So if I now look at my integral, so it was x cubed plus over 1 plus x to the power 8 dx, then I get the integral of x cubed, 1 plus, well, x to the power 8, well, if t is x to the power 4, then t squared would be x to the power 8, so it becomes a t squared there, and dx becomes dt over 4x cubed. And you can see here that the x cubes will cancel, which will leave me with the integral of a quarter, that quarter there that can come out to the front, 1 over 1 plus t squared dt. Now the integral 1 over 1 plus t squared is actually a standard integral and it's on your formula sheet. What you get is you get tan inverse. So that equals the tan inverse of t plus c, and if I then substitute back in what t is, t was x to the power 4, so I get x to the power 4 there plus c. Okay, so that was integration by substitution question, and that is the final answer for question 1. Okay, moving on to question 2. Okay, so we had two parts of this. So the fifth term of an arithmetic sequence is -6, and the 12th term is -34. So if we remember what an arithmetic sequence is, so arithmetic sequence is we start off with a value a, and then what we do is we add on a difference d every time we move up to the next level. Now I don't know why that's not right. Let's try that again. There we are. And so on. Okay, so you can see that if I wanted to do it for arbitrary n, it would be a plus n minus 1 d. Okay, so what I'm told is u5 is going to be a plus, well, 5 will be n, so 5 to the equal 1, so it'll be 4d, and that's going to equal my value -6. And I'm told u12, that's going to equal a plus 11d, and that equals -34. So I'm going to do simultaneous equations with these two here. So because my a's are the same, I can solve for d. So if I do equation 2 subtract equation 1, then a's will cancel. 11 subtract 4 is 7, so I get 7d. -34, take away -6, that becomes +6. -34 plus 6 is -28. I get d equals -4. Okay, and if we substitute the value, okay, use the first equation, then I would get a plus 4 lots of -4 have to equal -6. So a plus -16 equals -6. Add the 6 on the other side, you get a equals 10 there. So I found my two values. I found the first term, which is a, that is 10, and I found the common difference, which is -4, so it means that every time we go to the next number in the sequence, we are subtracting 4 to get that new number. Okay. However, we're going to obtain algebraically the values of n for which s of n is -144. So that means the sum of the first n numbers would give me -144 in this arithmetic sequence. We want to find how many terms would have to be in there to give us that sum. Okay, so I know from a question that a is 10 and d is -4. The equation I'm going to use, okay, it's written on the formula sheet. The sum of an arithmetic sequence is a half of the value n, then it is 2 lots of a plus n minus 1 d inside my brackets there. Okay, now I know my sum is going to be -144. That's going to equal a half of whatever n is. multiplied by 2 lots of A, that's 2 lots of 10, plus n minus 1, again we don't know what n is, multiplied by negative 4. Okay, so we've got a bit of tidying up to do here. So we get negative 144 equals, well, I'm going to deal with what's inside my main bracket first. So if I tidy up everything here, what that quickly comes down to is, well, 2 times 2 lots of 10 will give me 20. Okay, multiply this out, that'll be minus 4n, minus 4 plus, the times negative 1 will be plus another 4 there. So negative 144 equals a half of n times by 24 minus 4n there. Okay, so I've dealt with what's inside that bracket. Let's multiply this out and collect all the terms to one side. So that's going to be 12n minus 2n squared if I multiply that out. If I bring everything over to the left hand side, I end up with 2n squared minus 12n minus 144 equals 0. Okay, so that's what I'm going to be doing. That's what I'm going to be solving in order to work out what value of n this gave me here. So if I divide everything by 2, okay, first of all I can take a common factor of 2 and divide everything by 2. That gives me n squared minus 6n minus 72 equals 0. That splits up into two factors where I get two numbers to give me negative 72. If I multiply them as negative 12 times positive 6, that would also add up to give me negative 6 in the middle, so there are my two factors there. Solve for each, okay, so you'd end up with n minus 12 equals 0, n equals 12, n plus 6 equals 0, n would equal negative 6. However, we have an issue there because we know that n had to be positive due to it being the number of terms that we're talking about here. So n's a number of terms used, so you can't get negative 6 amount of anything regarding term wise. So n has to be positive, therefore we'll just keep the answer n was 12. Okay, so that was the solution to that bit there. Okay, so we worked out the n was 12. Okay, moving on to probably what the trickiest question was in the progress check was question 3. So the complex number z equals 2 plus I is a root of the polynomial equation, and it gives us the equation there. First job is to state the second root of the equation, and then we're going to use that to find the remaining roots. So the good thing is, and you can see it was only worth 1 mark, but the good thing is to get your answer to part A, you know the root z equals 2 plus I is a root, therefore the other root is z equals 2 minus I, okay, and that is known as what is called a conjugate, okay, where the sign in front of the imaginary part of a complex number is swapped over, okay. So if you know one root, then the conjugate is also a root, so we get the second root there. What we're going to do is we're going to use those two roots to start the process of calculating what the next root or the other two roots were. Now we expect 4 roots in total because we had a z to the power 4 polynomial. Okay, so what I'm going to do is I'm going to write these both as factors. Okay, so that means I'm going to bring them over to one side, so it'll be z minus 2 minus I from the first one, z minus 2 plus I from the second one. And what I'm going to do is, they're my two factors, I'm going to multiply them out. Now, it's up to you how you multiply these out. I think when you get into these types where you've got 3 in each bracket, a table can actually make things quite nice and succinct. So that's going to be negative I there. So I'm going to z minus 2 plus I there. And what I'm going to do is I'm going to just multiply each part against its own. Okay, so z times z will be z squared. Z times negative 2 is negative 2z. Z times negative I iz. Negative 2 times z is another negative 2z. Negative 2 times negative 2 is plus 4. Negative 2 times negative I is plus 2i. Positive I times z is plus iz. Positive I times negative 2 is negative 2 lots of I. And positive I times negative I is negative I squared. Now if you remember I squared, we'll start off with that, is the square root of negative 1. Then I squared is negative 1, so if I'm doing negative of I squared, that means I'm doing negative of negative 1. Two negatives become positive 1 there. Okay, you'll also see here in my table a lot of things do cancel out. So for example, negative iz cancels with positive iz, plus 2i cancels negative 2i. So these are my remaining terms. So the terms I get given when I multiply this out is z squared minus 4 lots of z plus 4 plus the extra 1 plus 5 there. Okay, so that's what those two factors produce when I multiply them together. I'm now going to use this, and I'm going to divide this into a polynomial to leave me with an expression that gives me my other two factors. Okay, so z minus 4z, z squared minus 4z plus 5, I'm going to divide that into a polynomial, which was, if you bear with me 2 seconds, rather than move up my page, I've got it written here, that was going to be z to the power 4 minus 6z cubed plus 16z squared minus 22z plus 15. Sort of regretting picking a question that's got tons of 2's and z's in it, but anyway. Right, so we need to now work out how many times that algebraic term on the left hand side can go into this polynomial. So if I multiplied the left hand side, or the divisor I should say, by z squared, I'll be left with a z to the power 4 term which I can cancel. Okay, so I'm going to times everything there by z squared. Okay, I'm just going to write that down here as well. So I'm going to times everything here by z squared, that'll give me z to the power 4 minus 4z cubed plus 5z squared. Okay, and I'm going to subtract everything there on the top line by this here. So the z4's cancel, z power 4's cancel. I'm left with negative 2z cubed. 16 minus 5 is plus 11z squared. The z parts didn't change at the minute, so they're still negative 22z plus 15. So I've managed to reduce my power from a z to the power 4 with a z to the power cubed. Okay, so my aim is now to still continue doing that. So I'm going to multiply everything here by a z to get z cubed. I'm also going to times it by negative 2, so I'll get the negative 2z cubed to cancel. So it'll be negative 2 lots of z that I'm going to times everything by here. Okay, so times everything by negative 2z, that's going to give me negative 2z cubed plus 8z squared minus 10z there. And remember, I am subtracting everything from here. Okay, so the z cubes cancel. 11 subtract 8 gives me 3z squared. Negative 22, take away negative 10 is negative 12z plus 15. Okay, so I'm almost there. I can still try and get my z squares cancelled, so I'm just going to times everything by positive 3. So if I times everything by positive 3, then I get 3z squared minus 12z plus 15. Okay, that looks like it's all going to cancel nicely. All of them will cancel. I'm left with 0. Now the 0 should happen there because I was using factors that I know solve this polynomial, okay, because they were roots. Therefore, that's not a surprise. So that should have happened. What I am left with though on the top is the function that I'm going to be looking at in order to find my new roots. Okay, so I'm given z squared minus 2z plus 3 equals 0. If you do the quadratic formula, okay, then you're going to see that z will equal 2 plus or minus the square root. Well, if you do b squared minus 4ac, you're going to get negative 16 in there. Not negative 16, my apologies. Negative 8 in there. Divided by 2. Okay, so that's what I get there. And we know from using complex numbers now that I can solve a root, even though it's got a negative in it, by making it root 8i over 2. And if you remember from surd, root 8 is the same as 2 root 2. So that can become 2 plus or minus 2 root 2i over 2. Divide everything by 2. I get 1 plus or minus root 2i there. So there are how you solve for the other two roots. The best thing to do at the end of a question like this, even though there's a lot of work involved, is just complete what all the roots were. Okay, so my first root was z equals 2 plus I. Then we had the conjugate, 2 minus I. Then from the last part we had 1 plus root 2i. and we'll have 1 minus root 2, and you can see there the conjugates of each other as well. Okay, so put that in a nice wee box for the marker to see it. So those are the solutions for those 3 questions there. Please have a look to check how your marks were given to you, and also if you didn't quite manage to get full marks on the question, you can hopefully copy down and see why that is the case looking at solutions. If you have any questions, always just ask. Thank you.